Hi, welcome to Project Geospatial. I'm Adam Simmons, and here with me for this episode of the Industry Limelight is Francis Doumet. Did I pronounce that correctly?
That's correct.
And we're going to be introducing Metaspectral. Francis, if you can go ahead and introduce yourself, give us a little bit of background before we dive into the conversation of who the company is.
Sure. Hi, everyone. I'm Francis Doumet, as Adam mentioned, CEO of Metaspectral. My background is actually in robotics and software for embedded systems. I initially got started on Metaspectral back when I was wrapping up my first startup. We were doing next generation push notification technology for mobile operators, so nothing to do with what we're doing now. At that time is when I actually met my co-founder, who was kind of freshly minted with this PhD in machine learning. And he had this really cool idea on how to use machine learning to optimize compression algorithms. So if you take your typical algorithm like JPEG, for instance, it just uses the same compression formula to each and every input. And it was chosen like that just because it worked best for the widest variety of image types. And so the idea here was to essentially tailor the compression tech or the compression algorithm to each and every input. And so we got started by kind of reaching for the low-hanging fruit first, which is static images and JPEG. And we essentially came up with, after a few months of work, of a machine learning turbocharged, if you will, JPEG algorithm, which essentially achieved like 30% more compression for the same quality than traditional JPEG. We tried to market it for a while, and you can go into that later if you like, Adam. But the long story short, we found there was a lot of competition in that area. It was a very crowded market, and so we started to look for more data formats which had more potential and had actual more solid and pertinent problems to solve. So we started going up the food chain of data formats, and that's how we started working on multispectral and hyperspectral data. And we found, that the technology has been around for a while, but it's just kind of started to take off now because of a few factors. The first one is the form factor of the imaging technology was significantly decreased, which made it possible to embed into aerial platforms or satellites. And the second thing was price. They're still expensive, but they've been getting significantly cheaper, that it's actually possible to embed in a satellite without impacting the cost too much. And as far as problems goes, we basically found out that, hyperspectral imaging, as most of you on this call might know, deals with a very large volume of data. And so it can be very taxing on both the imaging side, where data is collected, but also on the transmitting side, to transmit that data down to the ground and have it processed.
Awesome. No, thanks for that introduction. And just to go a little bit deeper, and so right now you're diving into more hyperspectral right now, or you're compounding on your compression algorithm a little bit more. So just give me an idea where your company is currently doing, what your maybe mission and vision is of what you're trying to do right now, and where you plan on going.
Yeah. So right now we're definitely long on multispectral and hyperspectral. Basically, the mission of the company is to accelerate advanced infrared systems. I forgot to mention earlier kind of what hyperspectral is for those who don't know, but it's essentially taking an image far into the infrared range. So a typical image just takes 3 frequencies, red, green, and blue. In hyperspectral, we go deep into the infrared range and take up to 300 different frequencies at the same time. And so as a company, we're developing both the hardware and software necessary to help stream, analyze, and store/index the data in real time.
Okay. And so how difficult, what kind of providers, and you don't collect your own imagery, of course. So what kind of providers do you work with, and what types of hyperspectral are out there? Is it just aerial providers? Is it satellite providers? Can you give us a sense of that?
Yeah, absolutely. So, we're just getting started. We've been around for a couple of years, and so the tech is near completion right now. And so we just started engaging with the image providers. And so the types of folks that we're connecting to include satellite manufacturers. So you have your traditional folks like Planet, which are more on the multispectral side of things. And then you have startups, which are actually the main force behind hyperspectral in space. Those guys are essentially building up their satellite constellation as we speak. Most of them are launching in 2022. And so that's our goal now as a company, is to be, or basically find a ride in space with one of these companies. In the meantime, we're working on the aerial side. And so we're working with a few operators of UAVs or UASs that are collecting hyperspectral imagery from the air. The most one of the partners, I guess, that we're working with currently is the Canadian military, and they're collecting a lot of hyperspectral imagery for persistent ISR applications.
Can you give us some use cases? What are some use cases you can talk about by, some of the best practices on how you've processed the hyperspectral imagery and how people can use this, just to tell people is like, hey, how valuable this stuff is?
Sure. So hyperspectral imaging is great to identify chemical compounds, and is very sensitive to chemical compounds and different types of surface materials. And so, as far as applications go, it's really great at detecting things that are invisible to the naked eye. For instance, for military applications, it's great at detecting camouflaged vehicles or camouflaged individuals. Because it's great at detecting chemical compounds, it's also great at finding IEDs, improvised explosive devices, on the ground from tens of thousands of feet in the air. And because we need this, because we're looking for very small things, typically it's like very, like a few inches of a camouflaged vehicle that might have the signature we're looking for, or a small IED from tens of thousands of feet in the air. We really need to have this high resolution, and this is also why it's very, or hyperspectral is very complex data format to deal with, because we gather such a sheer amount of data, and we're essentially trying to find needles in a haystack. And so, as far as our performance goes, well, maybe I'll take a step back and explain the challenges with that current operators have, Adam. And so, a single hyperspectral image can be in the gigabytes. And so,
probably tens of gigabytes, I imagine, actually, because a regular EO imagery could be, 2 to 5 gigs, depending how big it is. But hyperspectral is just loaded with data, right? So
yeah, it depends how many bands you gather and how long you fly. And so transmitting all that data down to the ground can be challenging. And so what a lot of people are doing, including the military today, is they actually keep all that data on board the imager, so on board the UAV, for instance, and do all the processing on board. Now, in order for you to do that, they still have to truncate the data because it's so massive. So they truncate it first, and then they feed it into a suboptimal machine learning algorithm, or even statistical analysis algorithm, for that matter, that that is able to run on the limited resources available on board. And that fails sometimes to detect the slightest spectral signatures that we need to detect an IED, for instance. So our approach is, instead, what we do is we decide to compress all the data losslessly on board the edge device, and we can compress it down to just a third of the size, again losslessly, and then we send it down to the ground in the bandwidth available, and then on the ground we have a big data center where we can use much more powerful machine learning algorithms to detect that data. To detect the targets. We can also do lossy compression as well. And so a big challenge that has existed in the past was every time people would try to do lossy compression, they would essentially decimate the data, which means essentially subsampling the data. And again, that would have the downstream effect of failing to detect targets on the ground. And so our approach is essentially if we're going to do lossy compression, to compress without decimating the data. And so we essentially are able to maintain the high level of both spatial and spectral resolution. And that way we're still able to detect all our targets. Just as an example, for the Canadian military, we were essentially testing the envelope of this system. How far could we go with the compression? And we managed to compress the hyperspectral data down to just 9% of the original size.
You said 90%?
No, just 9% of the 9%. Original.
There was a little hiccup in the sound. I was like, did I get that right?
Yeah, and they were still able to detect all their targets, even the ones that had the very small signatures in the first place.
So that's significant. So we're talking about So let's say something was an entire gigabyte down to maybe 100 megs.
Yeah, exactly. And so for for the military or anybody else, right? That essentially means you can move your human operator from a manned aircraft down to the ground and fly a UAV instead.
What are the typical file formats that you deal with hyperspectral, especially after post compression there? Yeah,
well, the market leader, I guess, in hyperspectral formats is L3 Harris, which developed a format called Envy, which is the same name as their software. That's, I guess, the typical format. It's really uncompressed data. It's just a data cube of 16-bit integers. When we compress it, we obviously compress it down to a format which we didn't invent, by the way. We compress it to a format that was developed by CCSDS, which is a consortium of space agencies around the world. It stands for something like Consultative Committee for Space Data Systems. It includes NASA and the Canadian Space Agency and the European one. And so anybody could in theory decompress it without needing any specific decompressor from our side. What we offer, however, is a high throughput and high fidelity decompressor in the case of lossy, which is essentially able to decompress as fast as we're able to compress. So essentially in real time.
Excellent. That's amazing. So just as mission data could be offloaded off the bird or off the satellite or wherever you're processing this stuff. So is there any type of limitations? How many images can you push through your pipeline at once? What's the what are the hurdles have you overcome as you're working on these problem sets?
Yeah. So right now, So as I mentioned, the algorithm itself was actually developed by CCSDS, and our IP is actually in the way that we've parallelized the algorithm to achieve high throughput and real-time capability. And so we're able to compress at about 37 gigabits per second. And so that currently is more than any hyperspectral imager can capture at.
Yeah.
But the bottleneck so far has been getting the data onto our compression module.
So it's the pipeline in between that's really more causing the issue from the bird before it even gets into your system, probably.
Yeah. And so we were an early version of the module was just connecting the camera to our compression module by Ethernet, which max can do 10 gigabits per second. That's if you're lucky. And so what we're moving to now is we're connecting the cameras directly to the memory of our compression module. And so as the images come in, actually as each line of an image comes in, because these are typically push broom systems where it's a scan system where each line comes in one at a time. As each line comes in, we scan it right away. I mean, we compress it right away. I'm sorry. And so that's how we're able to achieve much higher compression ratios that way. I'd say another bottleneck is obviously the downlink capability from space. So the vast majority of space objects kind of transmit down at about 1 to 200 Mbps, and so we are starting to see gigabit per second downlink capability on the Ka band, and that's going to become more and more prevalent. But
does this only apply to the processing and compression of it? This is also applied to the machine learning aspect of what you're doing to identify the objects. Is that those speeds include that aspect of it as well?
Yeah. Well, so the speeds I mentioned earlier, the 37 gigabits per second, that's compression throughput.
Okay.
And then on the machine learning side, it takes about 200 to 300 milliseconds to analyze an image. And so the question of doing real time ISR just depends on the bandwidth transmission time, and that's when the downlink bandwidth comes into play, and that's how much it's important, I guess, from a real time perspective.
Now, multispectral imagery or hyperspectral imagery, I should say, is a different beast when it comes to how much is available for doing training and labeling. How have you overcome some of the training and labeling aspects for the machine learning with such a niche area of the imagery community?
Yeah, it's a great question. So the way we've approached that is actually, traditional machine learning algorithms, they take the entire image as one sample. Right? They try to detect a hot dog or not a hot dog, right? In the case of hyperspectral, because we have so many dimensions in the third dimension, which is the spectral dimension, we actually do machine learning on a pixel by pixel basis. And so let's say like your image has 10 million pixels. That means we have 10 million samples. And so that allows us to do two things. First, it allows us to increase or drastically increase our training data set. So again, like a single image can give us millions of training samples. And then second, it actually allows us to do identification at a sub-pixel level. So we can identify what an object is, even if it's only part of a pixel.
Okay. That's impressive. So you just part. So we're talking about cutting off half the object as well, just seeing partial objects, not just to be able to identify it that way?
Yeah. So, let's say, you're imaging something from space and, excuse me. And the resolution is not large enough for you to be able to identify a car on the road. Let's say a pixel shows you 3 cars.
Okay.
We'd actually be able to at least tell you that within this pixel, there's 3 cars and there's a road and there's grass, all in that one pixel.
Okay. Well, that's incredible. I'd love to dive more into that at some point and understand, what the use cases behind that are and how you've managed to accomplish that. That's an amazing feat there, especially when most are just trying to struggle on even identifying a single object across an entire image. So,
yeah, and this has implications for instance, space domain awareness, right? And so we've been talking so far about imaging from space, but you can also do it the other way around. You can image from the ground up to space
and just see what satellites are up there and what's floating around, et cetera, right?
Yeah, and so when you do it from the ground, also your resolution is very limited. Like maybe a 20 millimeter dish on a satellite could be like just 1 pixel or half of a pixel. And so we can do the same thing. We can detect, how big that dish is from the ground, how many solar panels it has, what it might be able to generate in terms of power, and then ultimately detect what kind of threat it might pose.
So this to talk back on the overall company here, your target audience, to say it the way it sounds, is mostly getting in touch with the imagery providers themselves and helping them, or is it directly with the mission partners? Can you talk a little bit more about your business model for that, who you're trying to go after, and who ideally you'd like to be interested in your company?
Sure. Well, so far, in terms of industries, at least, the two main ones that have made significant headway in hyperspectral imaging have been defense and Earth observation. So those are our two key markets. We don't plan on getting into the hardware game and launching our satellites ourselves. At least
Well, when you say Earth observation, we're talking about agriculture, energy, mining. I'm assuming other than defense, you kind of can go into Earth observation from a commercial perspective and what that actually means and who your target audience is on that. So,
yeah, sure. So again, the Earth observation satellites are just kind of launching in between now and 2022. But the markets that have been identified for those, and some of them have already have contracts, go in are agriculture, mining, oil and gas, to detect leaks and methane emission.
To clarify, we're still talking about hyperspectral here, not everything else that's out there.
Yeah, we definitely are. We definitely are. I think the market is still, at least on the Earth observation side, it's still at the stage where the providers of these imagery is essentially training their customers on understanding what the impact of hyperspectral is. There's been this kind of breadth of academic research being generated on hyperspectral, but as far as commercial applications go, it's still fairly new, and so. This is happening right now where imaging providers are explaining to their agricultural customers how important this is to be able to monitor crop health from space, or the amount of moisture in your crops, or even detect like the ratio of weeds versus actual crop from space. Same thing on like forestry, for instance. Like using hyperspectral, we can detect. We can do like an ecosystem type breakdown of the flora. So, for instance, non-photosynthetic trees are more fire prone than photosynthetic trees, for instance. And these are things that only hyperspectral imaging can detect. Traditional EOIR can't do that. So, as far as our business model goes, we're first and foremost connecting directly to the providers of the imagery, since they are the ones that capture the images and have to send them down to the ground. And so our value proposition to them is fairly simple. Because we can stream the data down and compress it down to the size where it's streamable, we're essentially able to save them hundreds of thousands of dollars per year per satellite, just in transmission and storage costs alone.
Yeah.
So it's a win-win situation in that case. We're also approaching, I guess, more of the analytics providers, which tap into all this imagery and then do their own kind of analysis on top and then sell insights. Those are also a potential customer base for us, since they usually duplicate the data on their own servers, and because once they purchase them, they kind of want to keep it, for future use.
Well, so last couple of questions here in terms of scaling out the company. Is there any plans to do you, well, first of all, I think I have a question before I get to that one. Do you for your compression algorithms, do you do anything more than the hyperspectral? Do you actually does those compression algorithms work on the other imagery types, EO, IR, etc., standard geotiffs or NITIFs and things like that? Are you able to use that same unique compression algorithm to even make those more efficient?
Yeah, and that's it. Yeah, it's a great question. So we just started recently exploring SAR data, so synthetic aperture radar, and so we are able to process that data as well, and compress it down using very similar algorithms. EOIR is also very similar. We've also done actually this week we're ongoing a pilot with the Canadian military on EOIR as well. I guess that's it. Does that answer your question?
Yes, it does. And so I'm kind of curious of how do you want to scale out your capabilities and where you want to go with your company beyond increased customer base. What's your ideal scenario for Metaspectral?
Yeah, so we essentially want to be kind of the go-to provider for data analytics on hyperspectral data. So if you happen to be either a producer of imagery or even a analytics provider, you would come to us to either send us your data if you're a producer. So you would stream that directly to us, and then we would automatically run the machine learning algorithms, detect targets, and index all the data to make it retrievable in real time from an API. And on the other hand, if you're an analytics provider, you would be able to tap into that data, either purchase it or buy rights to it if necessary, and then be able to build other applications on top of it.
Okay, excellent. Is there anything else you'd like to say about the company, yourself for that matter, and experience before we wrap up?
Well, we're very eager to connect with the space community in general, Earth observation, or even aerial imaging for that matter. We very much love speaking to customers just to understand what their pain points are. And so if this conversation has piqued your interest at all, please do reach out. We just love connecting with customers and understand if there's anything we can add to our roadmap, which would solve like a real world problem for a lot of people.
How do people reach out to you?
Yeah, so you can email me at Francis, FRANCIS at metaspectral.com. That would be the best way.
Awesome. And we'll include that email address and how to get a hold of you in our show notes. Well, Francis, thank you very much for coming on and helping us introduce Metaspectral to our audience and talking about who you are and what the company does. I'm Adam Simmons on the series Industry Limelight, part of Project Geospatial. Thanks, everyone. We'll talk to you next time.
Thanks for having me, Adam.